Hello, and welcome to section 2.8, where we talk a little bit about curved arrows and how they're used, both how to use them and why we use them. So, curved arrows, as you can see here written in the notebook, are a little different than reaction arrows. So, if you remember from your general chemistry courses, reaction arrows are the things that take you from product or from reactants to products, and they're mostly just there to make that distinction, right? They don't actually do anything besides show what thing is being made and what thing is being used up. However, curved arrows serve a different role, and when we draw them, much like I just did, we're going to show how electrons move. And more specifically, we're going to show how electrons move in regards to resonance structures. So if you remember, again, from general chemistry, we talked a little bit about resonance structures. Perhaps you remember an example like this, where maybe you had a nitrate anion. It's an anion because we have to draw our formal charges in, positive on the nitrogen, two negatives on the oxygens to give an overall -1 charge, right? And in those general chemistry courses, what was said was that we can do a resonance form where we show how the molecule might exist based on which atoms might have a double bond and which ones might have a single bond. Because in the nitrate anion, you could move these electron lone pairs around to generate different resonance structures. We use our resonance brackets, and we can have this type of movement and make some other resonance structures as well. So if you noticed, we used these orange curved arrows to show how those electron motion actually happened. And that's exactly what we're going to do here, talking about curved arrows for resonance structures. Now, there are a couple easy rules to remember whenever you're doing or drawing resonance arrows. The first being only pi bonds move, pi electrons. Sigma electrons do not move. So we'll draw that in two. Sigma electrons don't move. And so that means we don't break sigma bonds. Okay, good. So that's our first big rule, and that's something that you should remember every time. That's rule number one. Number two is also important, which is don't exceed the octet rule for the following elements: boron, carbon, nitrogen, oxygen, fluorine, the second row elements that are in the P block, the main group there on the right. So don't exceed the octet, which means they must, at the most, have 8 electrons. And if they have more than 8, then you're in trouble. And that's when you know you have a bad resonance form. Okay? What does a good resonance arrow look like? In general, we can say a good resonance arrow, we should do it in green, because green is like go, right? Okay? We have this carbon oxygen double bond. A good resonance arrow starts either at a bond and goes to an atom like this, giving you this type of form, or, for instance, it goes from an atom to a bond to go back the other way. And we always put the resonance forms in their brackets like this. This is a good way to use a resonance form, or to use a curved arrow. A bad way to draw a resonance arrow would be to break some of our rules here. So bad uses. We'll call it bad arrows. Let's say we have this type of molecule. We have an oxygen with a negative charge and 6 lone pairs bound to a carbon with 3 alkyl bonds, 3 carbon-carbon single bonds. We cannot bring this bond down. If we do that, that's 5 bonds to carbon. That's bad. So remember to use the arrows correctly. Another example of a bad arrow is to, let's say we have this double bond, and we now break the double bond to make 2 very bad structures. You cannot break a single bond, this bond here. So that would mean this is bad. Okay, what are some other ways to do this right? So let's say we have an amide, which is this type of nitrogen attached to a carbonyl group, or what could be called a carbon-oxygen double bonded functional group, a carbonyl. This amide has a lone pair that can be brought down in between the nitrogen and the carbon. And the only reason why this is a good arrow, because if you notice, the carbon I've just marked in blue here will have 5 bonds if we leave it at that, right? The only way to leave it as a good use of an arrow is to continue bringing the electrons onto the oxygen to relieve that 5 bonded situation. So when you do that, this is the structure you get, which means that if this is the structure you get, this resonance form here might be stable, or it might not be stable. We'll talk about that a little more as we get down into the end of this chapter. But this is a good use of an arrow. Okay, a bad use of an arrow would be one that has the arrow pointed the wrong way. What does that mean? Let's try this again. So here we have a molecule that looks like this. A bad use of an arrow would be for them to go opposite. Instead of it going from a bond or a lone pair to a bond or an atom, instead it would go the opposite way. So if you draw it this way, then it looks like you are breaking a sigma bond. Right? That's what it looks like if you draw the arrow that way. The good way to draw it would be to draw it going this way. And because we had an octet issue here with this carbon, we had to move the double bond farther. Let's give ourselves a little more room here. There we are. So we'll go over many types of ways to use these curved arrows, but this is a good primer on how to start. Remember, the arrows have a head and a tail. So the head is here, and the tail is here. Arrows go from a bond or a pair of electrons, and they go to a bond or an atom. Always remember that. And this has been section 2.8.